In this video, I discuss limit problems that can be solved by suitable rewritings. These two graphs here illustrate that kind of situations. I start by a review of the subject matter. In limit computations, the undefined quantities 0 to the power 0, 1 to the power infinity, 0 to the power infinity, infinity to the power 0, and so forth cause problems because these are not numbers. We cannot assign a numeric value for these quantities, and therefore in several limit computation situations rewritings are necessary. In the evaluation of expressions arising in limit computations, one may use the following rules. Any number a divided by the infinity is always 0. Infinity times a positive number is the infinity, and infinity times a negative number is negative infinity. Main methods of limit computations are that if the function for which the limit needs to be computed is defined by an algebraic expression which takes a finite value at the limit point, then this finite value is the limit value. If the function for which the limit needs to be computed cannot be evaluated at the limit point, that is, the value is undefined, then find a rewriting of the function to a form which can be evaluated at the limit point. In the computation, one frequently needs a factorization rule. Most commonly used is a squared minus b squared equals a minus b times a plus b. Second method is to cancel out common factors. For instance, x squared minus 1 divided by x minus 1. First of all, we factorize the numerator, we get x minus 1 times x plus 1. Denominator was x minus 1, we cancel out x minus 1, we observe that x squared minus 1 divided by x minus 1 is simply x plus 1. And as x approaches 1, this quantity approaches the number 2. If a square root appears in the expression, then we multiply and divide by the conjugate of the square root expression. This conjugate is typically a sum or difference of square roots. So for example, square root of x minus square root of x minus 2 can be simplified for limit computations by first multiplying and dividing it by the sum of the square roots. Then one gets a square root of x minus square root of x minus 2 times a square root of x plus square root of x minus 2, and that divided by the sum of the square roots. Now in the numerator, the difference of the square roots times the sum of the square root then simplifies to first square root squared minus second square root squared, that is x minus 2, and that is divided by the sum of the square root. Now x minus 2 is simply 2, and that needs to be divided by square root of x plus square root of x plus 2. Now as x approaches positive infinity, the denominator approaches also infinity, and 2 divided by that approaches 0. So by this kind of a rewriting, we may conclude that the limit of square root of x minus square root of x minus 2 as x approaches the infinity is 0. Straightforward substitution in place of x would yield that as x equals the infinity, square root of x minus square root of x minus 2 is the infinity minus the infinity, which is undefined. Therefore, this rewriting was necessary. Overview of the problems to be discussed. First one, limit as x approaches 2, x squared minus 3 times x plus 2, and that divided by x minus 2. If we here substitute x equals 2, we get 0 divided by 0, which is undefined. Therefore, rewriting is necessary. Second problem, limit as x approaches infinity, x cubed plus x squared plus x plus 1, and that quantity divided by x cubed plus 3 times x squared plus 5 times x plus 2. Straightforward substitution here yields the infinity divided by the infinity, which is undefined. In problem 3, we have to compute the limit as x approaches the infinity of square root of x squared plus 1 minus square root of x squared minus 1. And here the straightforward substitution yields the infinity minus the infinity, which is undefined. In problem 4, we have a similar situation, limit as x approaches infinity, square root of x squared plus x plus 1 minus square root of x squared minus x minus 1. And here the straightforward substitution would yield the infinity minus the infinity, which is undefined. In problem 5, we have to compute the limit as x approaches 0 of 2 times x divided by square root of 2x squared plus x plus 1 minus square root of x squared minus 3x plus 1. Here, a straightforward substitution would yield 0 divided by 1 minus 1, which is also 0. Therefore, that is undefined. In problem 6, t approaches 0. The quantity is 1 divided by t times square root of 1 plus t minus 1 divided by t. In problem 7, x approaches the infinity, cube root of 8 times x cubed minus 1 divided by square root of x squared minus 1. In problem 8, x approaches 1 from the negative side, and we have to compute the limit of x squared minus 1 divided by the absolute value of x minus 1. In problem 9, we have to compute the limit as x approaches 5 of square root of x squared minus 9, and that minus 4, and this difference divided by x squared minus 6 times x plus 5. In problem 10, x approaches negative infinity. The quantity is square root of x squared minus 16 divided by 8 minus 2 times x. Here, a straightforward substitution would yield the infinity divided by the infinity, which is unknown, undefined. In problem 11, x approaches 0. The quantity is x to the power minus 3 plus 2 times x minus 2 minus x to the power minus 1, and that divided by x to the power minus 3 minus 2 times x to the power minus 1 minus 2. The last problem is problem number 12. Here t approaches 0. The quantity for which limit has to be computed is 2 divided by t multiplied by 5 divided by x plus t squared minus 5 divided by x squared. Clearly, we have to assume here that x is different from 0, because otherwise 5 divided by x squared would be undefined. Solutions to problems. In problem 1, x approaches 2. We have to compute the limit of x squared minus 3 times x plus 2, and that divided by x minus 2. If we substitute x equals 2, x minus 2 is 0, and x squared minus 3 times x plus 2 is 4 minus 6 plus 2, which is also 0. Therefore, direct substitution yields 0 divided by 0, which is not a number. Solution is to rewrite x squared minus 3 times x plus 2 is x minus 1 times x minus 2. That has to be divided by x minus 2. X minus 2 cancels out. We get that the quantity for which we have to compute the limit is actually x minus 1 in disguise. Hence, the limit as x approaches 2 of x squared minus 3 times x plus 2 divided by x minus 2 is the same as the limit of x minus 1 as x approaches 2, which is 2 minus 1, which is 1. To compute the limit as x approaches the positive infinity of x cubed plus x squared plus x plus 1, and that divided by x cubed plus 3 times x squared plus 5 times x plus 2, one has to divide both the numerator and the denominator by the highest power of x appearing in the expression. In this case, it is x cubed. One gets x cubed plus x squared plus x plus 1 divided by x cubed plus 3 times x squared plus 5 times x plus 2 is 1 plus 1 over x plus 1 over x squared plus 1 over x cubed, and that divided by 1 plus 3 over x plus 5 over x squared plus 2 over x cubed. And now each quantity having x in the denominator approaches 0 as x approaches the infinity. 1 over x becomes 0, 1 over x squared becomes 0, and so forth. Therefore, this expression approaches 1 divided by 1, which is 1. So the answer is the limit is 1. To compute the limit as x approaches the infinity of the expression square root of x squared plus 1 minus square root of x squared minus 1, one observes that direct substitution yields infinity minus the infinity, which is undefined. So the solution is to perform a rewriting. We multiply and divide the difference of the square root by the sum of the square roots. The expression gets now a little bit long. Square root of x squared plus 1 minus square root of x squared minus 1 becomes the difference of the square root times the sum of the square roots divided by the sum of the square roots. The sum of the square roots, of course, could be cancelled out, and then we would be back in the original expression. However, this rewriting is useful because the difference of the square root times the sum of the square root is simply the first square root squared minus the second square root squared. So this becomes square root of x squared plus 1, and that squared, minus square root of x squared minus 1, and that squared divided by the sum of the square root. Square root of x squared plus 1 squared is just x squared plus 1. Square root of x squared minus 1 squared is just x squared minus 1. Therefore, we get in the numerator rid of the square roots. So we had observed that square root of x squared plus 1 minus square root of x squared minus 1 is just x squared plus 1 minus x squared minus 1, and that divided by the sum of the square roots. In the numerator, x squared cancels out. We have 1 minus 1 left, so this expression is simply 2 divided by square root of x squared plus 1 plus square root of x squared minus 1. Here we may now substitute x equals the infinity. Then the numerator becomes the infinity, and we have 2 divided by the infinity, and by the evaluation rules, 2 divided by the infinity approaches 0 or is 0, therefore we conclude the limit as x approaches the infinity is 0. Problem number 4 is similar to problem number 3. We have to compute the limit as x approaches the infinity of the difference of square root of x squared plus x plus 1 minus square root of x squared minus x minus 1. Direct substitution here yields the infinity minus the infinity, which is not a number. Therefore, a rewriting is necessary. And the rewriting is, in this type of a situation, always that we multiply and divide the original expression, which is a difference of square roots by the sum of the square roots. So square root of x squared plus x plus 1 minus square root of x squared minus x minus 1 becomes the difference of the square roots times the sum of the square roots divided by the sum of the square roots. The expression now looks rather long and maybe somewhat complicated. However, in the numerator we have the difference of the square roots times the sum of the square roots. This is just the first square root squared minus the second square root squared, and that has to be divided by the sum of the square roots. So we have found the rewriting for the expression for which we have to compute the limit. That expression is simply square root of x squared plus x plus 1 squared minus square root of x squared minus x minus 1 squared, and that divided by the sum of the square roots. Of course, the first term is simply x squared plus x plus 1 in the numerator. The second term in the numerator is just minus the quantity x squared minus x minus 1. Therefore, we get simplification and square roots disappear from the numerator. Also, x squared cancels out. Then we have x plus 1 minus x minus 1. This is just 2 times x plus 2, and that divided then by square root of x squared plus x plus 1 plus square root of x squared minus x minus 1. So we have found the rewriting. Square root of x squared plus x plus 1 minus square root of x squared minus x minus 1 is 2x plus 2 divided by the sum of the square roots. We have to compute the limit of this expression as x approaches the positive infinity. The original expression had the problem that direct substitution yielded the infinity minus the infinity, which is not a number. Direct substitution in this rewritten version yields the infinity divided by the infinity, which is not a number either. So still a rewriting is necessary. We divide both the numerator and the denominator by x. Then the numerator becomes 2x divided by x, which is just 2, plus 2 divided by x. And in the denominator, we divide every term by x, but when we bring x under the square root, it becomes x squared. So we get in the denominator square root of x squared divided by x squared, which is 1, plus x divided by x squared, which is 1 over x, plus 1 divided by x squared, plus then square root of 1 minus 1 divided by x minus 1 divided by x squared. This is now a nice form for this expression for which we have to compute the limit. Because now, as x approaches the infinity, each term having x in the denominator becomes 0. And the limit is therefore just 2 divided by 1 plus 1, which is 2. So 2 divided by 2, and the limit is 1. In this problem, x approaches 0. The quantity for which the limit has to be computed is 2x divided by square root of 2x squared plus x plus 1 minus square root of x squared minus 3x plus 1. Here, a direct substitution yields 2 times 0 in the numerator, which is 0, and in the denominator we get square root 1 minus square root of 1, which is 1 minus 1, which is also 0. Therefore, the direct substitution yields 0 divided by 0, which is not a number. Here, the solution is to perform a rewriting in which we multiply and divide the whole expression by the conjugate of the square root expression. So this 2x divided by square root of 2x squared plus x plus 1 minus square root of x squared minus 3x plus 1 becomes 2x times the sum of the square roots, and that divided by the product of the difference of the square roots and the sum of the square roots. Rather long expression. Simplification happens, however. So we observe that we had now for the original expression 2x divided by square root of 2x squared plus x plus 1 minus square root of x squared minus 3x plus 1. We now get that in the form 2x times the sum of the square root, and that divided by the first square root squared minus the second square root squared. So this becomes just 2x times the sum of the square roots divided by x squared plus 4x. Now here x approaches 0. Even after all these rewritings, if we substitute x equals 0, we get 0 divided by 0, which is not a number. So in order to rewrite this expression that we have now obtained into a more suitable form, we divide by x. We divide both the numerator and the denominator by x. In the numerator we get just 2 times the sum of the square roots. In the denominator we get x squared divided by x, which is x, plus 4x divided by x, which is 4. And now if we substitute x equals 0, we get 2 times square root 1 plus square root 1, which is 2 times 2, which is 4, and that divided by 0 plus 4, that is 4 divided by 4, which is just 1. So we conclude the limit is 1. In this problem we have to compute the limit as t approaches 0 of 1 divided by t times square root of 1 plus t minus 1 divided by t. A direct substitution here would yield 1 divided by 0 minus 1 divided by 0, which is certainly undefined. It's not a number. So direct substitution cannot be used. We have to perform a rewriting. First we simplify, we combined the difference of the fractional expressions. We get 1 divided by t times square root of 1 plus t minus 1 divided by t is simply 1 minus square root of 1 plus t, and that divided by t times square root of 1 plus t. Then we multiply and divide by the quantity 1 plus square root of 1 plus t. That's the conjugate of the expression in the numerator. When we do that, the whole expression simplifies to negative t divided by t times square root of 1 plus t times 1 plus square root of 1 plus t. And t cancels out. This is just minus 1 divided by square root of 1 plus t times 1 plus square root of 1 plus t. And now we may perform direct substitution. Substitute t equals 0, one gets that the limit is minus 1 divided by square root of 1 times 1 plus square root of 1. So we get minus 1/2. To compute the limit as x approaches the infinity of cube root of 8 times x cubed minus 1 divided by square root of x squared minus 1, we observe that direct substitution first yields the infinity divided by the infinity, which is not a number. A rewriting is necessary. Here we have roots, but we do not have differences of roots that could be dealt with by multiplying and dividing by the conjugate expression. What one has to do here is to take under the cube root in the numerator x cubed as a common factor and under the square root x squared as a common factor. So the numerator becomes x times cube root of 8 minus 1 divided by x cubed. The denominator becomes x times square root of 1 minus 1 divided by x squared. Now the x terms cancel out. One gets that cube root of 8 times x cubed minus 1 divided by square root of x squared minus 1 is just cube root of 8 minus 1 divided by x cubed, and that divided by square root of 1 minus 1 divided by x squared. Now as x approaches the positive infinity, 1 over x cubed and 1 over x squared both approach 0. Therefore the limit is just cube root of 8, which is 2. So the answer is that this limit is 2. In problem 8, we have to compute the limit as x approaches 1 through numbers which are smaller than 1 of x squared minus 1 divided by absolute value of x minus 1. Here this expression x right arrow 1 and minus sign means that x approaches 1 but remains smaller than 1 at all times. We must make the observation that since x is always smaller than 1 and approaches 1, it means that x minus 1 is negative and approaches 0. And since x minus 1 is negative, this means that the absolute value of x minus 1 is just minus x minus 1. Here one has to pay some attention to get this right. So after this observation, we perform a rewriting. X squared minus 1 divided by absolute value of x minus 1 is just x squared minus 1 divided by minus x minus 1, which is minus x plus 1 times x minus 1 divided by x minus 1. X minus 1 cancels out. This is just minus x plus 1. Therefore, limit as x approaches 1 through numbers which are smaller than 1 of x squared minus 1 divided by the absolute value of x squared minus 1 is the same as the limit as x approaches 1 through numbers smaller than 1 of minus x plus 1, which is just minus 2. So the answer is that this limit is minus 2. This is an example of one-sided limits that will be discussed more in detail later. When we write under LIM x right arrow 1 minus sign, we mean that x approaches the quantity, the number 1, through numbers which are always less than 1. This is so-called left-hand limit of this expression. To compute the limit as x approaches 5 of square root of x squared minus 9 minus 4, and that divided by x squared minus 6 times x plus 5, one may want to substitute x equals 5 first. 5 squared is 25, so x squared minus 9 is 25 minus 9, which is 16. Square root of that is 4. So the numerator is 4 minus 4, which is 0. And the denominator is 25 minus 30 plus 5. When x equals 5, that is 0 also. So direct substitution x equals 5 yields 0 divided by 0, which is not a number. Rewriting is necessary. And we rewrite by multiplying and dividing by the conjugate expression. So we multiply and divide the whole expression by square root of x squared minus 9 plus 4. Then we get a expression which seems more complicated and longer, but the numerator simplifies to x squared minus 25, and the denominator is x squared minus 6x plus 5 times square root of x squared minus 9 plus 4. But still, after this rewriting, we are in the situation that direct substitution x equals 5 yields 0 divided by 0, which is not a number. So in order to deal with this situation, we have to factorize the numerator x squared minus 25. It is x minus 5 times x plus 5. So we have observed that the original expression for which we have to compute the limit is really x minus 5 times x plus 5, and that divided by x minus 5 times x minus 1 times square root of x squared minus 9 plus 4. But x minus 5 cancels out. So we are left with x plus 5, and that divided by x minus 1 times square root of x squared minus 9 plus 4. And here we may perform direct substitution. If we substitute x equals 5, the numerator is 10, the denominator is 4 times square root of 16 plus 4, which is 4 times 4 plus 4, which is just 32. So we get 10 divided by 32, which is 5 divided by 16. So the answer is that the limit as x approaches 5, or square root of x squared minus 9 minus 4, divided by x squared minus 6x plus 5, is just 5 over 16. To compute the limit as x approaches negative infinity of square root of x squared minus 16, and that divided by 8 minus 2x, we first observe that direct substitution yields the infinity divided by the infinity, which is not a number. So a rewriting is necessary. And the rewriting is such that from the numerator we take under the square root x squared as a common factor, and from the denominator we take x as a common factor. Now minus 16 does not have x squared in it, and 8 doesn't have x in it. So some violence has to be performed, and we observe that square root of x squared minus 16 divided by 8 minus 2 times x is just square root of x squared times square root of 1 minus 16 divided by x squared, and that product divided by x times 8 divided by x minus 2. Now x approaches negative infinity, therefore x can be viewed only as a negative number. We are interested in negative values of x. And square root of x squared is the absolute value of x. When x is negative, this is minus x. So we may assume that square root of x squared is just minus x for this particular computation. So we conclude that the original expression, which is now square root of x squared times square root of 1 minus 16 divided by x squared, and that product divided by x times 8 divided by x minus 2 becomes just minus x times square root of 1 minus 16 divided by x squared, and that divided by x times 8 divided by x minus 2. X cancels out. We get minus square root of 1 minus 16 divided by x squared, and that divided by 8 divided by x minus 2. And now we may perform the direct substitution. X equals negative infinity. 16 divided by x squared is 0. 8 divided by x is then also 0 when x equals the negative infinity, and we get minus 1 divided by minus 2. So the answer is that the limit is minus 1 divided by minus 2, which is just 1/2. To compute the limit as x approaches 0 of x to the power minus 3 plus 2 times x to the power minus 2 minus x to the power minus 1, and that divided by x to the power minus 3 minus 2 times x to the power minus 1 minus 2, we perform a rewriting. We multiply both the numerator and the denominator by x cubed. Therefore, the expression x to the power minus 3 plus 2 times x to the power minus 2 minus x to the power minus 1 divided by x to the power minus 3 minus 2 times x to the power minus 1 minus 2 becomes x cubed times the original numerator divided by x cubed times the original denominator. Expanding the products in the numerator and the denominator, we get 1 plus 2x minus x squared divided by 1 minus 2x squared minus 2x cubed, and as x approaches 0, 2x, x squared, 2x squared, and 2x cubed all approach 0. Therefore, the limit is 1 divided by 1, which is 1. To compute the limit as t approaches 0 of 2 divided by t times 5 divided by x plus t squared minus 5 divided by x squared, we first of all observe that x is a parameter. X is a fixed number, t approaches 0. And clearly x must be different from 0 because otherwise 5 divided by x squared would be undefined. So to compute this limit as t approaches 0, we must first combine the two fractional expressions in the second product. We get a rewriting. 2 divided by t times 5 divided by x plus t squared minus 5 divided by x squared is 2 divided by t times 5x squared minus 5 times x plus t squared, and that divided by x squared times x plus t squared. In the numerator, 5 can be taken out as a common term, and we get 2 times 5, which is 10, as one factor in the numerator. The second factor is x squared minus x plus t squared, so that is the difference of squares, which can be further factorized. So this is just 10 divided by t times x minus t times x plus x minus t, and that divided by x squared times x plus t squared. This simplifies further. We get 10 divided by t times 2x minus t, and that divided by x squared times x plus t squared. So here we have a rewriting. Our original expression for which we have to compute the limit as t approaches 0 is now 10 divided by t times 2x minus t, and that divided by x squared times x plus t. We observe that t cancels out. So we get 10 times 2x minus t, and that divided by x squared times x plus t squared. Now t approaches 0 and x is not 0. Therefore, we may now directly substitute t equals 0. We get 10 times 2x divided by x squared times x squared. So we get as the limit 20 times x cubed.